So, good morning students for the physical chemistry lecture, and for the last lecture you have learned the Gibbs free energy concept and Helmholtz free energy concept. Let us revise the relation between Gibbs free energy and Helmholtz free energy. Here you have studied the expression of Gibbs free energy as H it is equal G it is equal to H minus Ts, and for a system undergoing change at constant temperature the free energy change delta G is given by delta H it is equal to delta H minus T delta S, and Helmholtz free energy is defined as A it is equal to U minus Ts. For a system undergoing change at constant temperature, the Helmholtz free energy is given as delta A it is equal to delta U minus T delta S. But enthalpy change for a chemical reaction at constant temperature is given by delta H it is equal to delta U plus P delta P. And substituting equation number 3 in equation number 1, we get delta G it is equal to delta U plus P delta V minus T delta S. That is delta G it is equal to delta U minus T delta S plus P delta V. Since delta A it is equal to delta U minus T delta S from equation number 2, therefore we can write delta G it is equal to delta A plus P delta V. That is, the Gibbs free energy change differ from the Helmholtz free energy change by work of expansion, that is P delta V. That means this Gibbs free energy it excludes the work of expansion, that is mechanical work. So this Gibbs free energy it is more significant than Helmholtz free energy. Remember well, Gibbs free energy is more significant and more uh, accurate than the Helmholtz free energy change due to the Gibbs free energy it excludes the mechanical type of work, that is work of expansion. Then the significance of Gibbs free energy. A chemical reaction is governed by three important thermodynamic state functions. All of you know: enthalpy change delta H, entropy change delta S, and Gibbs free energy change delta G. The above three are related by the equation delta G it is equal to delta H minus T delta S. And this equation has a great significance as it decides the spontaneity of the process. For a reaction to be spontaneous, the free energy change must be negative. Remember that for every spontaneous process, the free energy of the process it decreases. However, the sign of free energy depends upon the sign of delta H and delta S. Hence, for distinct cases, they are as follows. Here, all of you know, for spontaneous process, delta G it is decreases, means negative value, and for non-spontaneous process, the delta G value is positive, and the entropy change for spontaneous process it is always positive. That means that reactions are endothermic, and the entropy change for non-spontaneous process it decreases. Then the change in enthalpy for exothermic reaction it is a negative, and for endothermic reaction it is positive. Then the reaction is spontaneous at low temperature. At that time, T delta S, it is less than delta H. And for non-spontaneous process at a high temperature, remember this temperature T, it is greater than initial temperature. Okay. Then for reaction is a non-spontaneous at low temperature. T delta S, it is less than delta H. Okay. Then we will see the today's point here. The variation of Gibbs free energy with temperature and pressure. That means how Gibbs free energy it varies with temperature and pressure. That means to show dG by dt it is equal to phi at constant temperature and dG by dt at constant pressure it is equal to T. Here all of you know the Gibbs free energy it is expressed as or defined as G it is equal to H minus Ts where H is the enthalpy of the system, T is the absolute temperature and S is the entropy of the system. Let it is our expression number 1 for infinitesimal change. Equation 1 can be written as dg it is equal to dh minus s dt minus t ds. By definition of enthalpy, we have u plus pp and again by differentiating this equation we can write dh it is equal to du plus pdp plus pdp and from the first law of thermodynamics we have internal energy change that is infinitesimal internal energy du it is equal to dq plus dw. If the work of expansion is occurred, then we can write dW it is equal to P dV. Therefore, here dW we replace by PdV and we have the internal energy change equation as dQ minus P dV. If the process is reversible, then for a closed system, we can write dq reversible it is equal to minus pdv and let it is our expression number 4 and dq reversible it is equal to t ds where ds is the infinitesimal entropy change for a reversible process. Substituting equation number 3 and 4 in equation number 1 we get dg it is equal to du plus pdv plus pdp minus dq reversible minus s dt and it is equal to dq reversible minus pdv plus pdv plus pdp minus dq reversible minus s dt and we uh, have here this dqr term with positive sign and here with negative sign. So these two terms get cancelled. Similarly, these two terms also plus PDV and minus PDV they get cancelled with each other. Therefore, we have PdP minus SDT it is equal to DG. Therefore, DG it is equal to PdP इकडे you know minus SDT. At constant temperature we have dP it is equal to 0. At constant pressure change in pressure it is equal to 0. Therefore dG equal to minus S dt. This term becomes 0 and the variation of free energy with temperature at constant pressure we have it is equal to minus S. This is the equation. Then the rate of change of Gibbs free energy with temperature at constant pressure is equal to decrease in entropy of the system. Remember the rate of change of free energy with temperature at constant pressure is equal to decrease in the entropy of the system. This is the significance of this equation. A rate of change of free energy with temperature at constant pressure, it is equal to the decrease in entropy of the system. Then at constant temperature, this term becomes 0. At constant temperature minus S dt, this term becomes 0, and we have dg equal to pdp. Therefore, the variation of free energy with temperature at constant temperature, it is equal to phi. Here it is the P, variation of free energy with pressure at constant temperature, it is equal to P. Thus, the rate of change of Gibbs free energy with respect to pressure at constant temperature is equal to increase in volume occupied by the system. Here there is a mistake. Here there must be P. That is dG by dP at constant temperature, it is equal to phi. And significance of this equation is the rate of change of Gibbs free energy with respect to pressure at constant temperature is equal to increase in volume occupied by the system. Then the Gibbs-Helmholtz equation and its application. What is the application of Gibbs-Helmholtz equation? We will see here. Here, the Gibbs free energy is defined mathematically or expressed as G equal to H minus Ts, where H enthalpy of the system, T is the absolute temperature, and S is the entropy of the system. And all of you know, enthalpy is defined by the equation H, it is equal to U plus Pp, and U, it is the internal energy of the system, P is the pressure, and P is the volume occupied by the system. Simply the difference is here. In your textbook, this internal energy, it is represented by capital E, and here it is represented by letter U. That is the difference. You may understand or you may take care. Then substituting this equation number 2 in equation number 1, we get G, it is equal to U plus PP minus S dt. It is our expression number 3. Then differentiating equation number 3 on both sides, we get here dg, it is equal to du plus pdp minus sdt minus tds. Okay. Again, from the first law of thermodynamics, for a reversible process, we can write internal energy du, it is equal to dq reversible plus dw. If the work is of expansion type, then we replace dw, it is equal to pdp. Therefore, du, it is equal to dq reversible minus pdp. And by the definition of entropy change for infinitesimal process, here small change in entropy ds, it is equal to dq reversible by t. Therefore, we can write here dq reversible, it is equal to t ds. Let it is our expression number 6. Then substituting equation number 5 and 6 in equation number 4, we get dg, it is equal to dq reversible minus pdp plus pdp minus dq reversible minus sdt plus pdp. That is dg, it is equal to pdp minus sdt. Then at constant pressure, we have dp change in pressure 0. Therefore, dg it is equal to minus s dt. And consider a system in which the following reaction occurs at constant pressure. Suppose A is our reactant, it produces B as a product. Let S1 and S2 be the entropies of the reactant and product respectively. And if G1 and G2 are the free energies of reactant and product, that means A and B respectively, then from the equation number 8 we get dg1 it is equal to minus s1 dt and dg2 it is equal to minus s2 dt. Therefore, dg2 minus dg1 it is equal to minus s2 dt minus s1 dt. That is d in a bracket g2 minus g1 it is equal to minus s2 dt plus s1 dt. That is dg it is equal to minus s2 minus s1 into dt. That is d of delta g it is equal to minus delta s into dt. Therefore, delta s it is equal to d of delta g by dt. Delta s it is equal to minus d of delta g by dt. But we have delta g it is equal to delta h minus d delta s. Then substituting equation number 9 in equation number 10, here we get delta g it is equal to delta h plus t, and substituting this delta s value d of delta g by dt at constant t. This equation is called as Gibbs-Helmholtz equation, and this term d of delta g by dt at constant p is called the temperature coefficient of the free energy change. Okay. Then the applications of Gibbs-Helmholtz equation. It is applicable for the calculation of delta G for all processes occurring at constant pressure. It helps to calculate EMF of the reversible cell. One can use this equation of a reversible cell for a reaction if the free energy changes at two different temperatures are known. These are the few applications of Gibbs-Helmholtz equation, and simply remember here the Gibbs-Helmholtz equation is the equation or relationship between Gibbs free energy and Helmholtz free energy. It is replaced and the enthalpy of the system. So, thanks for your patient listening. Study well, then stay home and stay safe. Thank you. We will see the next point later on.